Hi, my name is Kanishka, and I'm the team lead for Team CS903. I'll be taking you through our Capstone project. We have a jam-packed agenda, so let's get started. I'll be taking you through our objectives, followed by Utkarsh and Siddhan, who will present the literature review. I'll be back to take you through our approach, and then I'll hand it over to my colleague Elroy, who will go through the data sets we have used and experimental setup for this project. Bas will take us through the results of the fine-tuning tasks, and I will take us through the conclusions and discussion sections. As we're all aware, we are currently experiencing a boom in biomedical research, which means quite a lot of literature is being produced. This demands that more innovative approaches to biomedical text mining tasks should be investigated. At the same time, we are experiencing great advances in NLP using deep learning methodologies. Our project is focused in the biomedical and clinical text mining field, where we are using attention-based models to extract valuable information from biomedical corpus. Concretely, we are expanding on the research conducted by a team prior to us, where they pre-trained Albert on PubMed and PMC data, fine-tuned their models on 3 biomedical tasks, namely RE, NER, and QA. In continuation of that, we have pre-trained BioAlbert on clinical datasets, namely Mimic3, and fine-tuned this on various datasets where we have achieved results better than the current state-of-the-art models. However, before we do a deep dive into our approach, I would like to hand this over to my colleague Utkarsh, who will do a brief literature review. Over to you, Utkarsh.
Thank you, Kanishka, for explaining the scope of our project. So, as mentioned earlier, we are training attention-based models on biomedical corpus, and after reviewing 30 papers from different sources, we concluded that there have been various models that have been trained on biomedical corpus, and we'll be focusing on BioBird and Bluebird as they are quite similar to our model, and they'll be used as benchmark for evaluating the performance of BioAlbert, which is our model. And currently Bluebird is leading the race, followed by BioBird in attention-based models specific to the biomedical domain in the NLP community. From table 1, we can see that both are based on BERT architecture. Hence, we can conclude that both have the same advantages and limitations. We can also see that both have similar pre-training corpuses, with the exception being the PMC full text articles for BioBird and Mimic3 for Bluebird. We can also say that they have similar fine-tuning corpuses, and in table 2 I have compared a few of them with their respective tasks, and from the F1 score we can see that the Bluebird clearly outperforms BioBird and hence is currently the state-of-the-art model in the biomedical domain. And we have used similar data sets for our model for both pre-training and fine-tuning, and our model is based on Albert architecture. Now you might be wondering what's BERT, what's Albert, so I invite Siddhan to give a further explanation on that. Thank you.
Now let's talk about the literature review for the BERT and the Albert models. The BERT model has been derived from the transformers and the transformers will be used on the every layer across the model, whereas the Albert has been derived from the BERT model and it uses a parameterized sharing technique, which is not used in the BERT model. With the pre-training part, with the text corpuses they both use the same text corpuses, the book and the English Wikipedia corpuses. With the advantages, let's talk about the advantages the BERT has. The BERT can be fine-tuned according to the various tasks which we have, but in the Albert model, it uses a parameterized sharing technique. For example, we can explain it like this. So the steps, if they are as the BERT which carry out those tasks in 500 steps, the Albert model can do it in less than 200 or 300. And it also outperforms than the BERT because it's used the parameterized sharing technique. With the limitations, the both are computationally expensive, and also they perform poor on the domain specific tasks. With currently the Albert performs best in all the models which are currently available, and it's also the current state of art of model in the machine learning community. But it performs poor on various domain tasks. So we're going to use this on the biomedical field and going to train it or use it in the specific domain task. We can talk, and we're going to talk about it in the later part of the presentation. Currently, I invite Kanishka to talk about our approach.
Here I have outlined our approach. We pre-trained BioAlbert on Mimic-3 datasets, where we used the BioAlbert models to initialize the weights. This is a very compute-intensive process, hence we had to use Google Cloud TPUs. Then we fine-tuned the new BioAlbert plus Mimic-3 on new datasets. We also fine-tuned the existing BioAlbert models on the new datasets. We compared the results with Bluebird and BioBird as baselines.
As previously mentioned, existing BioAlbert model has been fine-tuned for some downstream tasks. Our goal is to add some new fine-tuned tasks to our model. In this project, we use Bluebird and BioBird as our benchmark model for the comparison of performance on new fine-tuned tasks. All datasets we use to fine-tune our model are from biomedical, clinical, and chemical domains. Some of datasets used on fine-tuned tasks may be imbalanced and small. It may affect the accuracy and variance of prediction. There are 5 tasks with 7 corpus datasets from Bluebird we used in fine-tuning our model, including NER, RE, semantic similarity, document classification, and inference tasks. In sentence similarity tasks, we train model to predict the similarity score of 2 sentences. The higher the similarity score, the closer are the sentences in terms of semantic meaning. Next, the relation extraction task is used to extract relationship of entity pairs from a text. We set up RE tasks as classification tasks, and each pair of entities will be classified into different categories. Entity pairs in a sentence will be converted to a mask token in our model. A word in a sentence may contain multiple relationships with other entities. Therefore, instead of feeding a sentence with multiple pairs to our model, we separate each pair of relationship into different samples and create multiple sentences as input. The third task we use is inference task. Given sentence of premise and hypothesis, inference task can identify whether the premise entails hypothesis. This task will address the problem in 3 ways, which are entailment, contradiction, and neutral. The next task we do is name entity recognition. Any out task is a task that classifies name entity mentioned in document into predefined categories. This name entity can be place organizations or specific objects. In this project, we define the labels of word into IOP format and measure clinical or biomedical terms from any out dataset. The last fine-tuning task is document classification. By classifying tests, we are aiming to assign 1 or more class into a document. In addition to BioAlbert model, our team also trained for BioAlbert model with Mimic dataset to obtain new models and fine-tune them for all the tasks mentioned above. We then compare the result of those tasks to our benchmark model. Next, our team member Bess will explain the result in details.
This slide shows the fine-tuning results on Bluebird datasets. We fine-tuned a total of 3 models, the previous team BioAlbert models, our BioAlbert models with Mimic-3, and the original Albert model. Yellow cells represent the best model. Red numbers represent where adding Mimic-3 helped improve BioAlbert models. Purple datasets are clinical domain datasets. Blue datasets are biomedical domain datasets. From the results, we can see that Mimic-3 only improved the performance of clinical domain datasets and slightly lowered the performance of biomedical domain datasets. This is because Mimic-3 is a corpus from clinical domain. In this dataset, we compare our Albert results to Bluebird results. In the Bluebird section, there's only 2 yellow cells. This means that most of our models outperform Bluebird. Therefore, we can conclude that our models have achieved the state-of-the-art performance. This slide shows the fine-tuning results on BioBird datasets. We fine-tuned our BioAlbert with Mimic-3 models on BioBird IE and NER datasets. These datasets are the same datasets that were used by the previous team. From these results, we can see that our models were able to outperform BioBird in most NER tasks. However, BioBird beat us in IE tasks. Unfortunately, we don't have large BioBird models to compare with because in the BioBird paper, they only fine-tune base model.
In this section, we'll discuss our results. In the next 2 slides, we have presented our results for 4 different data sets, where the red color represents BioAlbert, yellow is BioAlbert with Mimic, and blue is of course Bluebird. Overall, we've achieved some great results for BioAlbert with Mimic, as we have beaten some state-of-the-art models, specifically Bluebird, on clinical data sets. Furthermore, we have achieved great results on BioAlbert tasks, and we have also been able to beat Bluebird. However, the main trend that we can see here is that our Mimic model has become very specialized and only performs well for clinical data sets. And you can clearly see this from the next slide, where as we have trained our Mimic model and the fine-tuning, the pre-training steps have made it very specialized, because we only initialized the pre-training model with the BioAlbert weights. Had we had access to the pre-training data for BioAlbert, for example, if we had access to PubMed and PMC, then we could have trained both, taken all these data sets, combined them together, specifically PubMed, PMC, and Mimic, combine them together, and then pre-train BioAlbert. We would have had much better performance. It would have been much more versatile model. Currently, as it was initialized with the BioAlbert weights, and then pre-trained specifically with Mimic, which is clinical data set, as the pre-training steps went ahead, it had 270,000 pre-training steps for the large models and 200,000 pre-training steps for the base models. They became specialized and they perform really well on clinical data sets. However, they don't perform very well on other general tasks such as ChemProt or chemical data sets or any other data set that is not clinical. So in conclusion, pre-training on domain-specific corpus clinical data sets improved performance on downstream fine-tuning tasks. As a result, our models achieve better results than state-of-the-art in some instances. Our models did not perform well on non-clinical data set, as it became too specialized as the number of pre-training steps increased and the effective initialized weights vanished. I think future work for Albert can be, we can use PubMed, PMC, Mimic data sets, and if we combine all of these at the pre-training step, it should improve the performance of these models on a vast majority of the tasks. That's it. We have some extra slides, and thank you very much.